Good afternoon. Thanks, Greg, for the invitation to talk at the symposium. And thanks, Ron, too, for presenting some of the material I'm going to talk about. I'm going to, I guess, reinforce the message. So the first thing I'd like to say is that, I'm talking on behalf of a large consortium, what we call the Center for Injection and Seismicity Research. Let's see. Okay. Yeah, that's a very large consortium, sponsored by about 30 companies, small and big companies, midstream and producing companies, the Railroad Commission, as well as the New Mexico Oil Conservation Division are also sponsors of our work. So I'm going to give you a flavor of what we do. You can see a long list of contributors on the left-hand side of the slide. A lot of people working in that field. So I'm not going to show you result of personal result, but the results of the group. So you've seen that picture maybe shown by Ron before. So here, the title of the slide was, how are basins formed? And I think it's important to understand how the various layers come together, so you get a better feel of why what's happening is happening. So I'm going to use that terminology, the Delaware Basin on one side, the Midland Basin on the other side. So you have shallow Midland, deep Midland, shallow Delaware, and deep Delaware. As Ron mentioned, we have the deep and shallow interval. And typically the industry is producing from that gray area on the map in here, the Wolf Gap. And those basins came to be basically because of plate tectonics, as explained by Dr. Ward this morning. When you have plate colliding or passing each other, you end up with trough and ridges, and you basically erode the ridges and fill up the trough with sediments, and that's what we see. The Delaware Basin, 20,000 foot of sediments, and a bit less in Permian Basin, in Midland Basin. So I would like just to give a quick overview, extremely quick, saying oil is formed, because that's also important to understand what's happening in the basin. So initially, that's kind of inspired from what's happening in how the Permian Basin is. So I put in here the basement. Dr. Ward mentioned the basement this morning, saying it's highly deformed and not those things. So that's extremely important to understand why we have earthquakes in the state. It's because the basement is extremely deformed with a lot of faults and weakness zones. So when you have the seawater, invading the continent, and in the case of the Permian Basin, you have first carbonate. Then, tens of million years later, you have some shale, and then some sandstone. Now, typically, the shale are enriched in organic matter. And another characteristic of shales, they are very low permeability. They're kind of clay. So they have a lot of water in them. They have a lot of organic matter. And as the shale goes down, being buried, by the other formation on top of it, the temperature and the pressure increase, and that transforms the organic matter on oil. But the oil, so that's kind of the oil, is represented by those black dots. So you see on the slide on the slide at the bottom, I didn't put dots everywhere because the upper part of the shell wasn't exposed to the right temperature and pressure yet. But it is, in slide number 4, if you want. And then at some point, the pressure increases enough to push the oil out, which is, in any case, naturally buoyant. It's more buoyant than water, so it would move up and then accumulate in reservoirs in formations like limestone or sandstones, which have a high permeability. So you have basically two types of locations where you can find oil in the Permian Basin, on any basin in general. It's the shales that we call the source rock, which is the initial location of the oil, and then the reservoirs. And in general, you have a lot more oil in the source rock that hasn't left the reservoir yet. So, And so in the past, I said, as mentioned by Ron, you get the conventional, so you can see the, operators were producing by the sandstone, the Delaware Mountain Group on top in here, and producing and re-injecting the water in the full cycle, or going further down in the carbonate of the Ellenberger. So that's a type of conventional system. And then later on, like 15 years ago, operators, fracking the Wolfcamp and the Bone Spring, but injecting the water in a Delaware Mountain Group or in the Ellenberger. So that's what we call the unconventional thing. So, as I said, that shales in between the two permeable interval has a lot more oil than was ever produced from the reservoirs. So that's why it's interesting to go after it, and we were able to do that only when the industry was able to develop, the horizontal well technology as well as the fracking technology. So, okay. So here, the plot on the left show the production from conventional wells versus unconventional wells. So you can see it's extremely, starting from the 60s. So here is a production from the Permian Basin, at that time peaking in the 70s and then going slowly down. At the same time, the amount of water being produced increases, as also mentioned by Ron. But here, showing the extremely, basically extraordinary rate of increase in production of oil in the Permian Basin due to fracking here, and as well as water. So, and you can see that in that map in here, showing the in red, you have the conventional wells. So typically the source rocks are in the basin, and then they move up into the edge between the basin and the platform where they are trapped. And that's why most of the wells are all around the edge of the basin in here, the conventional wells. And then now the operators are going after the source rock, through horizontal wells in blue, or vertical wells, but long fracked vertical wells in the Midland Basin. We was the first basin in the Permian Basin that where operators were active. But you can see also that there is a few red dots, in both basins, because the operators went also after those kind of shallow pods of oil in those basins. Okay, so here is some numbers, to put on, on what I just said, showing the production, from the past 7 years in here. So the oil production increasing to 6 million barrels per day. This is about the production of Canada. This is almost the production of Russia, the production of, Russia is probably like 20 millions. The US too is about 20 millions, but it's a huge chunk of the oil produced in the world coming from the Permian Basin. And at the same time, you have the water production, and here, as you notice, the ratio between those two is probably 1:4. So now, what about re-injection? So now if I put the water injected back into the basin in the injection wells, is here. It's less than the water being produced, because a significant part of the water being produced is recycled from the industry. It's treated, into what's called clean brine and used for fracking again. So and so that how much of the fracking needs are covered by the recycling? Well, it's increasing through time. Here is in blue, you have the needs for fracking. And here is the recycling of the company, done by the company, and in red, you have, the groundwater needs, or what would be used by the industry from the groundwater. Typically, the industry will use brackish water, not fresh water, although they did use fresh water early on. So I would like to point out, too, that the amount being produced, the amount of water being produced in the Permian Basin, it's an outlier. It's way too much compared to any other basin in the world. It's for some reason, especially the Delaware Basin, produces a lot of water. And one way we compare the various basins is what we call the water-oil ratio, which is kind of equivalent to the water cut, if you have heard that before. So, Delaware is 5 barrels of water per barrel of oil, Midland 3, Eagle Ford in South Texas is 1.4, the Bakken in Dakota is 1.5, and the other shale plays, are mostly gas plays, so they produce almost no water. You don't even need to worry about the water being produced by them. So the Delaware Basin in particular is truly an outlier in the world of oil production. And one of the reasons that might be is because the thickness of the sand package, you have 5,000 feet of shale of clay, and so the water hasn't been able to be drained from this formation like it did in other basins, so you end up producing the water. And, all the problems we're having right now. So, but that high water cut is not distributed, randomly. There is a pattern to it. And the pattern is, as you go towards the center of the basin, the water cut or the water-oil ratio is higher. So if you are lucky enough to have your assets, on the edges of the basin, your water-oil ratio is lower. But, it turns out that the TDS of the water at the center of the basin is lower. So sometimes it's even lower than that of seawater. So, and as you go to the edges, it's higher. I mean, there's a bunch of reasons for that, but that's a little bit out of the scope of this meeting. So that's basically what you need to remember, that the water-oil ratio much higher in the center, but the TDS lower. And that particular map in here is showing the various wells. In yellow, we have the shallow wells, so a well injecting in the shallow formation, and in purple, the deep wells. So they are mostly in New Mexico, and those wells in here in Texas, have been shut down because of earthquakes. So basically, deep water injection occurs only in New Mexico right now. And that's why we are having this problem in the Delaware Basin, because all the water that used to be injected, deep, now it's all shallow. So, and why did we do that? Because of earthquake. So I don't need to belabor this. Yeah, let me skip to here, to the earthquake. So here is a map of the earthquakes, up to magnitude 5. So magnitude 5 is something you can really feel. Even magnitude 3 you can feel. I don't know if you live here, you probably have felt one of these, and they are particularly common here, in Culberson County. That's where we have the highest magnitude earthquakes. You have a few also in here in the Midland Basin. So that particular plot in here shows in the past 10 years, the amount of earthquakes detected by the network, the TexNet network. So that was put in place around here. So you see the huge jumps in earthquake, which is totally timed with the rise in injection. So there is no doubt about that, the fact that earthquakes, are due to the injection. And you do have earthquake elsewhere in the state, like Eagle Ford too, but they don't have that massive amount of water to inject. And same thing in Haynesville in East Texas. They're mostly, the Eagle Ford, the oil play, but yeah, it doesn't produce as much water. So here is a projection and a cross-section along the New Mexico-Texas state line, showing all the various formations. So the dotted line, the red dotted line, represent the limit between the basement and the sediments, and the yellow dots on top represent all the injection wells in the DMG, the Delaware Mountain Group, or the San Andres. All the blue dots in here represent all the wells being fracked, and here all the wells injecting in what we call the deep horizon, which is below the Wolfcamp, between the horizon being fracked. So you can see in here, and then all the red dots, the black dots, represent all the earthquakes in here. So they are typically in the basement. Some of them are shallower, they may be due just to the fracking itself, but that's fairly uncommon. They are typically due to injection. So here is that zone that we call the Culberson, Mentone zone, with a lot of earthquakes, very high earthquakes. It's not exactly clear what we have earthquake there, but all those zones in red in here represent some areas that have been being looked after by the regulatory agencies. Oops. How can I get rid of this? I don't know. Okay, here we go. So here, so that's what they call the Railroad Commission called one seismic response area. So they ban basically any deep water injection in this area, and then the earthquakes kind of stop, because there's still a lot of earthquakes happening, but not as much as in the past. And there are several of those SRS, like around Midland and Odessa, and there is a few of those zones too in New Mexico. And so here you can see in blue is the number of earthquakes in the Delaware Basin and versus the injection. So you can see that disconnect, because now all the injection is happening in the shallow formation, not in the deep formation. And same thing in the Midland, but you have less of an impact because the number of earthquakes was never that high. So what happens when you inject those fluid in a reservoir, in a formation already full of water? Well, you get overpressure. And those maps kind of represent, the amount of overpressure. That's the results from modeling we do. They do the calibrated models using all the information we can. And it turns out that the increase in pressure can be, it's certainly higher than 500 PSI. It can be, we're talking in general, not at the well itself. The well itself, the pressure can be 1,000 PSI on top of the initial formation pressure. But here we are, if you shut in all the wells, at once, and wait a little bit, you'll get that 500, 600, 700 PSI increase, which is, 10 to 15% more than the initial formation. So that 700 PSI is a lot. So even if an older well was plugged and abandoned according to the regulations, like 50 years, they may not withstand, that increase in 500 PSI. And so that's truly a problem. Another problem in terms of understanding why we have earthquake is what we call distal earthquakes on the right-hand side. This is a deep formation. In blue, you said the pressure increasing through time. And all the earthquakes, are at least 20 miles from the closest injection. So it's not very clear what we have that. You may have some fast pathway, some what we call poroelasticity, but it's not specific to the Permian Basin. We see the same thing in the Barnett, in the Fort Worth Basin. We see the same thing in Oklahoma. So it's a fairly common observation that you get earthquake far away from the injection wells. So that means nobody is really responsible for those earthquakes, and everybody is. It's just the general buildup in pressure, causing that problem. So now, since all the water is being injected at the surface, you may have that type of problem. And here's a map on the left, show basically all the wells with the age they were drilled. So on the Saltwater Basin platform, at the edge of the basin, where all the traps are, they are, it's mostly from the 50s in here, and some of them too in the basin. But most of them are a bit more recent, but they're still fairly old, and at least 30 or 40 years. So that's why we are having all those problems there. I'm not going to talk too much about that either. And switching to something maybe more interesting, or something we haven't heard yet, it's the surface deformation. How much uplift or thinking of the land we have in the basin. So we do have updated maps of these, but I don't have them with me here. So this is between, where is the date? Between here. This is the uplift or the thinking of the Earth between 2016 and 2022. So here is the Delaware Basin. So in kind of purple, deep purple, you have the land thinking by 4 centimeters. Same thing in a Midland Basin because of the production. So much oil is being produced that you get that thinking. Except you see that the kind of anomaly here at the New Mexico-Texas state line. You have here the land surface, moving up. So why do we have that? Well, we have it because all the operators in New Mexico are sending their water into Texas. And so that's why it's basically, just on the state line in here. And that's certainly a problem. I think agencies are talking about it, but so far nothing has happened. So, and here is something, a specific case. So you can look at the INSAR work, like in general, what's going up, what's going down, but you can also zoom in on a particular area. Here in this particular area, I think it's Loving County or Ward County, where you can see, very localized uplift of the water, of the soil, and that's what we want to study, to better understand what's happening. It can be used as a monitoring tool to see if something can or will go wrong if we don't do anything. So that's the end of it. That's between 21 and 24. So going back in time. So that's the way it was in 21. So what those slides are showing is, the uplift at this point in red, or that red diamond and blue diamond, they are here. So that blue diamond at the end has about 60 centimeters of uplift. That's a lot, but 2 feet of uplift. But that's not something you can notice at the surface. I mean, when you stand there, you don't feel it. But it does have a big impact on the integrity of the wells in that area. So there was 4 leaking problems in the footprint of that map. So here is one. Here, it's not clear what had happened, but it did. And then, as the pressure is increasing, as shown by that line in here, so we are here, the pressure increasing. I mean, the uplift increasing in here, probably that was a sign that event 2 was about to happen. You were able to see it before, ahead of time, because the land was, being lifted just at that location of the well. And then we keep going through time, then another well leaking in here, and not related to those 2, but I mean, probably related somehow, but not clear how. And then you have another event, close to that one, and then, the problem was kind of fixed, and then the land starting, thinking a little bit more. So we can do that type of study. So, there's a paper about that's published data. I can send it to you if you want to. There is no secret about it. But that's the type of thing that the regulatory agencies are looking at now. They are very interested in that INSAR work in terms of being able to predict where the next problem might be or might have been, so you can act, before it happens. And for example, here, I mean, this is the Central Basin platform, not the basin, but you can see there is a dot in here. It's here. So here there is 10 centimeters of uplift in that area, very, very localized. There is something happening there. So you just go there, you check the wells, and you make sure that there is no leak before it happens. So that's kind of the new thing regulatory agencies are looking into with our help at UT and other organizations. So here is basically the conclusion. Large surface increase due to water injection. Pressure increase can be very high. Seismicity is not a problem anymore, although we do have earthquake from time to time. But shallow injection is really a problem. So I say, although well, even it's plugged correctly, may still leak because they are not made to sustain, that type of pressure increase. And INSOR is going to help hopefully. And then there is a capacity challenge. The industry is keep producing more and more water. So we can reuse it, but for fracking, but that's fairly limited. The industry is almost there. We can treat it, but then even if you treat it, about half of it has to be injected because you cannot go a full solid, like go all the way up, because what do you do with the solids? You put it in a landfill, but that's even worse. If there's a leak in a landfill, you are going to contaminate everything. So injection is still needed. And now the industry is looking at, sending the water outside of the basin, the central basin platform, which is, under pressure in places, or the shelves, but that add, cost to the whole thing. So with that, I'll take any question. Ron? Yes, they go, because they stop injecting at the bottom. Seismicity was due to the kind of triggering the deep fault in the basement, and so now there is no injection, so there is no real, there's just residual seismicity, but it's going to go away. But it doesn't mean that you cannot have, high magnitude earthquake like you just had a few months ago, like magnitude almost 5. So because it's hard to understand how earthquakes happen, because yes, that's some modeling will show that. Yes, that's true, and you still have some seismicity on the top in the Delaware Mountain Group, the sandstone on top. But typically the magnitude of the earthquakes is kind of related to the size of the fault, and you do have hundreds of small faults in the Delaware Mountain Group, but they are nothing like the one you have in the basement. Those are huge thrust faults, from the continental collision way back, as described by Dr. Ward. So yes, so you still do have earthquakes, but that's not the issue. Not an issue for the regulatory agencies, as far as I can tell. And not really an issue for operators either. The issue is more capacity. What are we going to do with all that water? So, from a private vendor called B3 Insight. They are a partner to our consortium. So they may have it on their website. It's possible. They don't try to sell that type of, what they sell is just the individual well data, so that overall data. It may be on their website, I don't know, but yeah.
Any more questions?
Okay. Yeah. Oh.